Number 6 is a Gauss-Jordan, and that's very similar to the echelon method, except instead of a triangle, I want this diagonal. Now, the way I show it is a little bit backwards from the way I've seen it in the past. Basically, we want numbers along this diagonal here, and we want zeros elsewhere, okay? So some teachers will have you get the ones here first. We want ones here, and then zeros elsewhere. I'm going to have you get the zeros first, and then we'll worry about the ones later. Okay, so that's a little bit backwards from what I've seen it before. Regardless, we're going to start with this element of the diagonal, and that is called our pivot element, and we're going to try and use it to knock out these two right here. So we've got to come up with a rule, and since we have ones, it's really not so bad. We need a rule to knock out this -1 using this one right here. It looks like we should just be able to do like row 1 plus row 2 would give me 1 plus -1. That would be 0. And so I don't need to touch the top row. My top row is okay. That pivot element 1, I need a number there anyway. I'm not trying to change it. What I'm trying to change is this number right here. And so I use this rule, but I have to do all 4 columns. This one, this one, this one, and this one. I have to use my rule for all 4 of those columns. Row 1 plus row 2 is going to be 0. And then row 1 plus row 2 is going to be 0. Row 1 plus row 2 is going to be 1. Row 1 plus row 2 is going to be -1. Interesting. But we have to have another rule. We have to have another rule to knock out this one. So we're going to use our pivot element to knock out this third number, and so we have to have another rule. It's going to be 2 minus 2 is what we need. If I do row 3 minus 2 row 1s, that would give me 2 minus 2, and that would be 0, and that's what I want. Okay, that's going to be a 0 right there. But I have to use this rule right here. I have to use this rule all the way across each of the 4 columns. So same rule, I've got 2 minus 2 of these guys would be 2 minus 2 is another 0. And I've got this one minus 2 of these is actually going to be plus 2. It's going to be 3. And then I've got this one, 15 minus 2 of these 9s is minus 18. 15 minus 18 is -3. So this one is actually kind of a strange result because I want numbers along this main diagonal, and I can already tell right now that's not going to happen because I don't want this 0 right here. That's basically the problem. Okay, but regardless, I can kind of find a solution here somewhat because I can tell right here what this means is z equals -1. If you go all the way across this bottom row, that means 0x plus 0y plus 3z equals -3. Well, that's not necessary. I've got 3z equals -3, or divide by 3. I've got z equals -1, just like I had. Basically, that's what the second row said. Okay? So I know z equals -1, but the problem is I don't really know what x and y are, and that's what's represented in these 2 columns here. So it turns out that this one is many solutions. There can be a lot of different values of x and y, but this one has many solutions. So if you had to find kind of an idea of what a general form of the solution is, you might start by looking at that bottom or that top row and say x plus y minus z equals 9. But we already know z's value is -1, so that's going to be x plus y plus 1 equals 9, or x plus y equals 8. And so the solution is going to have to fit with this equation. So you can see a lot of different numbers, like x could be 2 and y could be 6. That would work. X could be 10 and y could be -2. Both those things add up to 8. And so both of those things work. This is why there are many solutions. So sometimes we have to find a general form. In this case, normally it would be x, y, and z, but we know the z value is -1. what we could do is take our equation, x plus y equals 8, and we'll use y as a parameter, meaning the variable we want to see. And so I'll just solve this for y, subtract x. I've got y equals 8 minus x. That's not what I wanted to do. I want to subtract y, sorry. I want x equals 8 minus y. That way I'm only looking at one variable. This is the general form of my solution. And so you can kind of tell by plugging in a number. If you pick a number like, let's say y was 6. If y was 6, x would be 8 minus 6 would be 2, and z, of course, is -1. That's just 6. So that would be one specific solution of the many.